All right, so let's find the moment of inertia about the y-axis. Before we get started, just remind you that moment of inertia about the y-axis is defined as x squared dA. And as I mentioned before, since we're going about the y-axis, we're going to try a vertical block. So let's think about a differential area that looks something like that. And just remember that our y value is easily obtained. I'm sorry, x value. So what would be the differential area for that? Well, how tall is it?
200 minus y.
Right. So it would be 200 minus the y value given by the equation, and it's dx thick. So what is the y value given by the equation? It's that. So that ends up being 200 minus x squared over 50 dx. So then the moment of inertia about the y-axis would be the integral of x squared dA, which is 200 minus x squared over 50 dx. And also in the x direction, this is going to be from what to what? Well, we're going to go from minus 100 to positive 100. So, as far as I'm concerned, the problem is solved. Of course, we have to do a little more work to actually get the result, but basically the problem is solved. So what does that turn out to be? So the first one is 200x, so that would be 200x cubed over 3 minus x to the 5th, divide by 5, already got, so that's 250. And you just need to evaluate that from minus 100 to 100. You can see the numbers are going to get quite large for this because we're in millimeters. I went ahead and kind of worked on this problem a little beforehand, so I know that when I evaluate this at 100, I get 26,666,666. And then when you do it at minus 100, you get minus 26,666,666. So when you put that all together, you get 53,300,000 and something. I'll just write it this way. 53.3 times 10 to the 6th, and that's going to be millimeters to the 4th. It's just, if you take your time, you can run those numbers through.
Pearson can't wait to count off for us millimeters to the 4th.
Oh, probably, yeah. They would love that. Now, I'm going to say or, and we'll do it again. A different way. The or part, I think I'm going to redraw this just so we can you can see it easily. So there's x and y. There's the shape. Not as nice as the one they drew. But let's do a horizontal strip, just as an example, an alternative. And remember, we're doing y bar, so now this becomes kind of that formula that we talked about before. The the y cubed, the x cubed dy over 3. Now, given this way, I've got an x distance here and one on this side, another x distance there. And it's going to be dy thick. So by definition, my differential value should be, what should it be? X cubed, well, the total distance x cubed over 3 dy, right? Now what is x? X is these two things put together. So what are those two things? I'll just do it this way. It would be really 2x prime cubed over 3. So that gives me the total length. Okay, and what's x prime? Well, I have to rewrite this equation for x, so I'll multiply 50 to both sides and take the square root, so I get the square root of 50y. You guys see that? Oh, I made a mistake. I just realized something. Yeah, this is not 3.
Is it 2?
It's 12. It's that one on the far side, because you'll notice that the axis that we're using is in the center of the block.
So is that the one we should always use? BH cubed over 12, or
no? Well, it depends on the situation. If the axis is at the bottom of the rectangle, you use 3. If it's in the center, you use 12.
What's so magical about 12?
It's because you move the axis to here, so it changes the moment of inertia. It gets actually smaller, right? Because now you're rotating about this axis. You can see there's less area distributed than there was about this. There's a lot more area up here. So see, they have the same numerator, BH cubed. BH cubed, once divided by 3, once divided by 12. We can derive that later if that's a...
Plus your moment arm smaller, does that have anything to do with it?
Say that again?
Plus your moment arm from that axis is smaller, like when it's at the
yeah,
bottom?
Yeah, usually it would be smaller. Right? The biggest moment arm would be h over 2. The biggest moment arm here is h. And then everything is cubed. So it gets even worse, or squared. So I may not expect you to remember that, but I just wanted to show you that if you did want to try it this way, you could. And it looks like a big mess. But it actually turns out to be not so bad. So if I integrate this thing, what do I get? I get the integral of all that. So maybe it is worse than I thought. Let's see. There's a 2 cubed over 12. 2 cubed is 8. 8 over 12 is 2/3. So I take care of that right off the bat. Then I put this 50y, square root of 50y in there cubed. So I get the square root of 50 cubed is what? That's 50 times the square root of 50. And then I got y, square root of y cubed would be y to the 3/2. Oh, and I left out I left something out. What did I leave out? No, I think that's it. Let me check my notes, make sure I did that right. I think so. So, resultant, it's not so bad. And then we're going to integrate in y, which is from 0 to 200. So what is that? Let's see. I can combine all that. So that's 100 over 3 times the square root of 50. That's all constant. So I'm left with just this. I can integrate that. So that'll be y to the 5/2 divided by 5/2. And then evaluate all that from 0 to 200. So it looks like a mess. But you put 200 in there and do all that calculation, And believe it or not, you get the same number. So it is possible, say in most cases, to go either way. But you can, I think the first option in this problem was the easier of the two to deal with. Somebody check that for me? I'm looking at my notes here. I think that's what I got. Anybody check that? It's okay? So again, looking at option A, vertical block, option B, horizontal block, it works about the same, but it did require that you have to know this, whereas if you don't worry about the second option, then the problem is pretty much straightforward. Questions?